today talk a little bit about just uncertainty, and from my perspective, so I'm kind of operations research on the border of economics, and so I'm very interested in the normative perspective, decision-making perspective, and so think a little bit about uncertainty, why we want to model uncertainty, and then some definitions of things like uncertainty and risk and objective and subjective uncertainty, and then the basics of the comparative statics of uncertainty in learning. So that's something I've been interested in, is how is the optimal decision changed if we have increasing risk, or how is an optimal decision changed if we expect to learn more? And then we'll apply that specifically to climate change and look at how, say, the optimal abatement in climate change changes as we're more uncertain about the damages. And then I'm going to switch gears a little bit and talk about the role of technology in the climate change problem, and then do a brief overview of the literature. And so we'll start here. So what are the reasons for specifically modeling uncertainty? When we, let's see, we have uncertainty in decision making. So we want to think about optimal decision making, optimal policy. There's uncertainty. Why do we want to explicitly model uncertainty? Fairly straightforward, but what are some of the reasons?
It can change your decision.
So it might change your decision, that's right. So if you explicitly model uncertainty, it might change your decision. So why are some of the reasons that it might change your decision? Okay, so one is risk aversion. All right, so one reason is that there's risk aversion. Okay, and that's what, probably in economics, a lot of people think of that one first. And so it might change your decision. But why else? You might have a decision maker who's not risk averse, but we still want to model uncertainty.
We can still have a flaw of averages. So the idea that when we average something, it doesn't give us the same answer as if we broke it out into pieces.
Okay, so the flaw of averages, and so I have a slide on that so I can explain exactly. But the idea here is if the thing you care about, right? So you have a random variable, and then the random variable affects something that you care about, whatever your objective is. And if that objective is not linear, then the expected value of that objective will change depending on risk. Okay? What else? What's another reason we explicitly want to think about uncertainty when we're modeling our decision problems? There's another good reason for it. I mean, it may be related to the flaw of averages, but
Costing.
What is it?
Costing.
Costing?
Yeah.
So meaning in what sense?
With respect to long run and short run costs, like a marginal cost, the cost of doing it now as opposed to doing it later.
Okay, so it might kind of affect our costs. Again, might be related a little bit to flaw of averages. Anybody else think of it? It's really how does it sometimes change our near term, the things we even think about doing? Might be irreversible, okay? We think of irreversible decisions, and so, or on the other hand, if it's kind of not an irreversible decision, I think what we're trying to get at is there's downstream decisions, right? Or sometimes what are called options. And so if you think of downstream decisions or options, those really change the way you think about things. And so you want to explicitly model uncertainty in those cases. And so I just have a few slides about these. And so we have risk aversion, which everyone's pretty familiar with. And so maybe just briefly, so what is risk aversion? Anyone want to tell me what's risk aversion?
That we prefer a certain outcome with the same expected value.
Right.
That has, will accept a lower expected value that's more certain than a higher expected value.
Okay.
That has greater uncertainty.
That's right, the basic thing. And then how do we generally characterize risk aversion? We're trying to model it. We tend to characterize it by a very specific risk premium. Okay, that's one measure. Kind of along the lines.
Decreasing marginal returns?
The decreasing marginal returns, right. And so I guess the way I think of it, right, so the way that I think of it specifically is a concave utility function, right? So risk aversion has to do with concavity. And this is pretty simple, right? This is kind of econ 1 or maybe econ 2 or something. But it turns out this is actually kind of important as you keep thinking about risk and changes in risk. This idea that concavity is a representation of risk aversion turns out to be important. Okay, and so we have the picture here. And doesn't be drawn very well, but you know, the basic idea is if we have, if you guys can see, if you have a concave utility function over your outcomes, then that, you know, if you, the expected utility, if you take the expectation of these 2 points, you get a point down here, whereas if you take the utility, you get it up there. Okay, so concavity has a lot to do with risk aversion, and so we'll run into that again. And then I have options, and so this idea of options, we use the word option, it comes from stock options. And so it's somebody in finance, so what's a stock option? What is it, a call option? What's the definition of a call option? What?
Possibility, but not obligation to buy.
Okay, right, the choice but not the obligation to buy stock at a certain price in the future. So stock option is a downstream decision. You can make a small investment now that gives you the option, and then in the future, when uncertainty has been revealed, when you see the actual price of your stock, you then have a downstream choice to either exercise your option or not exercise your option. So that's a very specific one. But there's a lot of downstream decisions. The one I have there is, you guys may have heard this, like a parking garage example, where you're thinking of investing in building a parking garage. But meanwhile, they're thinking of building a new baseball stadium a couple blocks away. So, but they're not sure yet. So if they don't build the stadium, you'd really like a 4-story parking garage. And if they do build a stadium, you'd really like to build a 20-story parking garage, because you would fill it up. And so the question is, well, what do you do? Okay, so one option you would have would be just to wait and find out if they're going to build the parking garage or not. And so that's one. Another option you might have, instead of building a 4-story garage, or building a 20-story garage, or you could build something halfway in between, but instead of doing those things, what you might do is build your 4-story garage, but build it extra strong so that if they decide to build the stadium, you can then add your 16 stories on top of it. Okay? And so the point being that because there's uncertainty and you explicitly recognize the uncertainty, you do something in the near term that you would never do otherwise, right? You'd either build an appropriate 4-story garage, which isn't super strong, or you build a 20-story garage, but now we're doing something in between. And so that's a reason that uncertainty is important, because you have these options. And then the one that Morgan pointed out, the Flaw of Averages, which is kind of the Jensen's inequality, right? But just this idea that if the thing we care about, if F is what we care about, so X is our random variable, F is what we care about, if it's not linear, then the expected value of F of X is not equal to F of the expected value of X. You can't just take the mean and plug it in. And so this is this Flaw of Averages word is from Sam Savage, and this is just a nice little example that I always like. So here we have one where the random variable is where the drunk is in relation to the center of the road. He might be on the center of the road, he might be off the road. And on average, he's weaving back and forth, so on average, he's in the center of the road. And so if you plugged in his average location, he's fine, he's alive. But in fact, his average state is not alive at all, because there's a very nonlinear payoff. If you're on the center, you're good. If you're off the center, you're dead. And so we need to think about these things. And so, my next thing here. So these are, you know, a lot of the ideas of why do we incorporate uncertainty, risk aversion, options, flaw of averages. And so kind of, you see kind of there's something that all of these have in common. You see, what do they all have in common? And it really comes to the flaw of averages kind of makes it the most clear, right? That if it's nonlinear, you have a problem. If it's linear, you don't have a problem, right? So what these all have in common basically is nonlinearity. Then in risk aversion, we have a concave utility function. In options, actually I didn't really show that picture, options also, they induce a nonlinearity, and the flaw of averages is just about nonlinearity. So if everything is linear, if we're perfectly linear, then actually you don't have to worry about explicitly modeling uncertainty. Then you really just need an expected value, and you can use that to make your decisions. But if there's any kind of nonlinearity, then you need to explicitly model uncertainty. And the reason is precisely what someone said at the beginning, because that can change your optimal decision. So as long as there's nonlinearities, we can change our optimal decision. All right, so we want to explicitly model uncertainty. So now we can talk a little bit about different, maybe kinds of uncertainty. All right, so this is something that you may have heard before.
Before you, I was wondering, why do you restrict yourself to expected utility theory?
Well, okay, that's true. I guess I'm going pretty.
Otherwise, I mean, it might have problems with nonlinearity, even if you have linear function.
Even if everything is linear. Yeah, so that I have. I'm mostly thinking in terms of expected utility theory. So mainly taking kind of the normative position that if you agree with those various rules, then you would want to maximize your expected utility. But you're right, you might, so non-expected utility, but it would induce a kind of nonlinearity even if things were linear. Right, so it's still along the same lines, so the problem is still kind of the nonlinearity that's induced. And it's similarly, you can start out with the options. Everything can be linear, you can be risk neutral. There's lots of linearity, but just the option itself induces a nonlinearity, so it's the same kind of idea. All right, so just briefly talking about probability and this idea of subjective versus objective probabilities. So a lot of times people will talk about objective probabilities, and that's really related to the frequentist interpretation of probability. And the idea is there are events which somehow happen frequently. They happen over and over again. And so we take the probability of this event happening as its relative frequency. And so the whole theory of probability started with things like rolling dice. And so you have dice, and they're very regular. They're all even. You can roll them very many times, and you do see that on average, a 1 comes up about 1/6 of the time, and so on. And then you can, to some degree, something like weather, where you get certain things come together, and they come together very often, and so you can kind of look at the frequency of that. So people will often call that objective probability. And so that's fine. But then you run into things that you're interested in that don't happen frequently. And so that's supposed to be a picture of a nuclear meltdown or something like that, right? So this is something we care about, we want to make decisions about, we want to know if our nuclear power plant is going to melt down or not. But it doesn't happen frequently. So you can't really go and take a frequentist approach. And so in this case, you have to switch over to what's called kind of subjective probability. And it's a different way of thinking about probability, which is really we call it just a degree of belief. So you can't, or you don't want to, build a number of nuclear power plants and then turn it up a little bit too high and see how many of them melt down. So we don't want to run experiments with this, and so we just have to kind of think it through. And we have experts and people who know a lot about it, and they'll have a degree of belief that something might happen. And you can use this probability in the exact same way you use a frequentist probability, and it has very similar ideas that if you say it's got a 90% chance of happening, that's very similar to spinning a dial that has, a 90% chance of landing on white. So we have these two issues. And so I guess one question that I've always had, kind of a philosophical question, is there actually a well-defined distinction between objective and subjective probability? People talk about them a lot, and it's somewhat useful to think about, but I guess to me it's not clear that there's actually a well-defined distinction between these two. Right? And it's for a few reasons. One is even in the kind of simple case of a coin or something like that. So we're all pretty familiar with coins, and we feel pretty confident that a coin is, you're going to flip a coin, it's 50-50. But in fact, I didn't bring one, but I could pull out a coin and I could start flipping it, and you don't really know if my coin is a fair coin. So there are things that are not fair coins. And so we could test it, but then the question is how many times do you flip this coin to know what the probability of the coin is landing on heads. So you could flip it 100 times, you could flip it 1,000 times. If it is a fair coin, then we think if we flipped it 1,000 times, it would come up heads about 500. But we wouldn't be super surprised if it came up heads 505 times, right, or 512 times. So then the question is, is your probability 0.5, or is it 0.505, or 0.512? So really, even with coins to some degree, it's really a degree of belief. Okay? We're not going to actually be able to test a coin and see if it has a 0.5 probability of coming up heads, because eventually, you flip it enough times to get to infinity, your coin's going to start changing. It won't be the same coin anymore. And then there's this whole idea that actually, if you're talking about a particular flip of a coin, it's a particular flip of a coin, right? It's either going to be a head, it's going to be a tail. It's not going to be 50-50. It's going to be one or the other, and if that's a particular flip of a coin. And so I actually don't think there's a well-defined distinction between objective and subjective. It's kind of interesting to think about these two different ends, and we kind of know what we're talking about, but it's really hard to say, well, this particular event has objective probabilities, and this particular event has subjective probabilities. Because really, they're all just along a continuum, and they're really all subjective in some sense. We know a lot more about some of them, we can agree a lot about some of them, but they're basically subjective probabilities. And then just, yeah, so I argue that these are really similar. And then also just this point that, I mean, I guess maybe everyone's familiar with here, but that something doesn't have to be varying to assign a probability to it, that anything can have a probability assigned to it, it can be fixed, it can be known by some people, but not known by other people. We can assign a probability to it. And that's like, for example, we could assign a probability distribution to the number of letters in my middle name. And so I may know that, and there's a fixed answer to it, but you guys don't know it. So if you had to make a decision about it, you would need to come up with a probability distribution over the number of letters in my middle name. And so we can do that. That's a random variable, even though it's fixed. All right, and then similarly, this idea of risk versus uncertainty. Now, there's a number of people seem to define risk and uncertainty in a lot of different ways in different literatures. But there's one of them, this idea, this is kind of like, I think, this Knightian uncertainty, where risk is when an event occurs with some kind of a measurable probability, and uncertainty is when the likelihood of the event is indefinite or incalculable. Okay, and again, you probably get a sense from the idea that I don't really think there's a big distinction between objective and subjective probabilities. I also don't think there's a clear distinction between these. So I don't know.
I just wanted to add that we had a very hard time within the IPCC. We were trying to give glossary definitions of this term, two terms, and basically risk for most of the people on this planet has also a negative connotation, whereas for economists, risk is either good or bad. So, and this is something, I mean, you can take, it can be an opportunity. Risk is something you can gain money from. And so it was amazing having in a room scientists and economists and psychologists, how everybody has actually a different perception and definition of these two terms.
Right.
Even whether these are good or bad things, it's incredible how hard it is to find.
Right. Yeah, and this is only one. I mean, this is a distinction that some people make. There's the other one that has to do with uncertainties, like the probability, and risk is when you put the outcome with it or something like that. And that's just a completely different definition. So I'm not talking about that definition, but this one here, I mean, again, because people, you know, there are compound probabilities. I mean, so that's kind of the one is if you represent something, you can represent it as a compound probability, and then that's kind of closer to uncertainty than risk, but not exactly. But again, I just don't think there's a strong distinction between these. If once you accept subjective probability is a degree of belief, then you can put a probability on any event. You might be more or less confident about the probability on that event, but
So just to follow up, so I think that risk really carries two distinct meanings in slightly different communities. So in the pure decision-making context, you think the economists talk about decisions under risk, the decision where there's a well-defined probability distribution of all the outcomes, and therefore you can do calculation of expectations and so on. Whereas uncertainty, the level of uncertainty can consider second order or higher order uncertainties, and therefore such calculations are impossible, at least not in principle. And whereas the other issue of risk in real life really is a combination of the probability and typically, but not always, negative consequences. So I think that these are two ways in which the word risk is used interchangeably and really with some confusion.
Right. Yeah, no, I agree with that. But again, but I'm kind of saying I don't really believe it's impossible ever to make an expectation over the probabilities, because I think if you need to make a decision, you're facing something uncertain, you just have to come up with subjective probabilities for that. You may be uncomfortable, you know, it may be hard versus flipping a coin where none of us have to think about it very much. But I don't think there's actually a strong distinction between those. So that's my own personal philosophical point of view, and so you might want to think about it, but also I'll point out, so when I use risk and uncertainty, I'll define them a little bit later very explicitly. I use those interchangeably, and I particularly talk about increasing risk and increasing uncertainty, and so for me, those are the same things. I just want to point that out, that I don't have this idea of these kind of impossible to assign uncertainties. Any other comments or questions about that one? Okay, so that's like the kind of basics. So now what I'm going to talk about is stochastic dominance, because this is really the way we think of increasing, it's one of the ways to think about increasing risk, and then this comparative statics of uncertainty in learning. And so this is really the question that I was interested in originally, and so given that there's uncertainty around climate change, a lot of people would like to know, well, what's the role of that uncertainty? So this is all a precautionary principle and so on. Does the fact that there's uncertainty in climate change mean that we should be more aggressive in fighting climate change? Or does it mean we should be less aggressive in fighting climate change? Okay, so this is kind of a question that people have been asking for a while. So this is a comparative statics question. What does it mean? If there's more uncertainty in climate change, do we reduce our emissions more? Do we reduce our emissions less? And so this is the question that I was interested in. And then there's a related question which says that if there's uncertainty in climate change, but we expect to learn, what role does that play? And so if we expect to learn more sooner, again, do we fight climate change more aggressively or less aggressively in the near term as we expect to learn more? And so these are kind of the basic questions I was interested in. And then also, I'm interested in technical change. And so as we learn more about climate damages, do we invest more in technical R&D or less in technical R&D? As we expect to learn more about R&D, do we invest more or less? So these are the questions that I was interested in. And so now we can talk about a little more explicitly, again, what I mean about riskier or an increase in risk. Okay, and so what I'm sure many of you have ideas. So what does it mean for one random variable to be riskier than another? There's a number of different ways you can define it, but who wants to come up with an idea?
One would be about the mean preserving spread. One variable is mean preserving spread of the other is riskier than the other.
Okay, so that's the kind of basic. Better pens here. So one is just this idea of a mean preserving spread, and so we can talk what that means. I mean, a lot of times when you talk about a mean preserving spread, you mean something along the lines of this. If we have one random variable, that's distribution looks like that, and then if we have another one that looks kind of like that, it's a mean preserving spread, and we say it's riskier. Okay, there's some other definitions for increasing risk. Some are equivalent and some are not equivalent. So what else besides just this idea that it's got more weight in the tails? How else might we define one random variable as riskier than another? Okay, so variance is another one. What else? Any other ideas about why we would say one random variable is riskier than another?
Certainty equivalence is higher.
Okay, the uncertainty equivalence is higher. And so that's related to the utility function then, right? Okay, and so the way, in this one in particular, the way I always think of it is that it's if all risk averters would prefer one random variable to the other, so if all risk averters prefer X to Y, then we would say that Y is riskier. Okay? It's kind of defined within itself, but it kind of makes sense, right? We've got a definition for risk aversion, people who don't like risk. So if all risk averters prefer X to Y, then Y is riskier than X. Okay? So it's another way of defining riskier. So these are all different ways of defining it. Let me see. I have my little slides here. And so that's that first one I have. I kind of like that because that seems the most basic, right? That if all risk averters prefer y to x, then x is riskier. Okay, and so that's if the expected utility of y is greater, so again, I'm in expected utility theory here, but the expected utility of y is greater than expected utility of x for all concave u, then we say that x is riskier than y. Okay, another one is that this is really the kind of classic definition for the mean preserving spread. So where I have down there the distribution G has more weight in the tails than the distribution of F, and we say G is riskier. And so this is this picture here. And then specifically the way that that is defined is this integral condition up there, where it says, let me see if I can draw. So if we look at cumulative distribution functions, and so we have this is some cumulative distribution function, and then we have another one that's riskier. See if I can draw it. If it kind of starts up higher, and it can cross, I have it right there, but if you start the distribution that starts higher, if the area between the curves when it's above is greater than the area between the curves when it's below, so if this area here is always greater than that area, then it's a mean preserving spread. Okay, so the idea being that we have a higher probability here of the lower, so this is where we want to be farther to the right. We have a higher probability of these lower outcomes. As long as this area is larger than that area, then it's a mean preserving spread. So it's a way of having more weight on the tails. It's just getting a very specific definition of what this means. And so if we look at these pictures I have here, the red line is a mean preserving spread of the blue, and the yellow is a mean preserving spread of the red. The green actually doesn't have the same mean, right? You can tell that the mean is not there, so it's not a mean preserving spread. It is, you can see that it's riskier though, right? Because its payoffs are lower, so we would often call that riskier. At least it's riskier than the red and the blue. It's not clear with it's not clear with the yellow, right? Because the yellow has a higher probability of some low outcomes. So we're not quite clear what we prefer between the yellow and the green. Okay, so it's a mean preserving spread. And then, there's another one that we didn't talk about, this idea that if x and y have the same distribution, except for that x has extra noise. So, I have it up there explicitly. No, so if we have x is equal in distribution to y, so x is a random variable, y is a random variable. These are equal in distribution, but plus there's some extra noise added to y, and then the exact requirement is that the expected value of that extra noise is equal to 0 for each y. So that's also another way of thinking of risk, right? So you have two distributions that are the same, but one has noise. It seems like it's riskier. And then the last one is that x has a larger variance than y, and that's one that we kind of typically think about. So I don't know if anybody's familiar with these. 3 of these are equivalent, and 1 of them is not equivalent. Is anybody familiar with which one is not equivalent? Which one of these things is not like the other? The fourth one, right? So the variance, it turns out, even though variance is the way that if people think about risk very much, they tend to think about it in terms of variance. It turns out that it's not actually equivalent to these other 3. And so you can have a random variable x that has a larger variance than a random variable y, but some risk averters will still prefer y. Okay, and you can think of examples pretty easily, right? If you think of a normal distribution that's centered at 0 and has a variance of 1, and then you can think of a random variable that has a 50-50 chance of a payoff of 1 or minus 1. You can imagine that a fair number of risk averters would strictly prefer plus 1, minus 1 versus a normal distribution that has these very, very large negative outcomes. And so then you can imagine that if you had, 1 1.1 and minus 1.1, a fair number of risk averters would prefer that. So its variance is larger, but a number of risk averters would prefer it. And so variance is not kind of strictly a great representation of increasing risk. Now it is in some cases, so if you're just comparing normal distributions against each other, then a normal distribution with a higher variance is riskier than another normal distribution. In fact, if you have any distribution that has just two parameters and you compare them to each other, then the one with the higher variance is also riskier. But you can't in general, just because something has a higher variance, it doesn't generally mean that it's riskier. And so those top three are often called the Rothschild-Stiglitz definition of increasing risk. And so again, this is what I'll use when I talk about something getting riskier or more uncertain. I mean by the Rothschild-Stiglitz representation of increasing risk, or a mean preserving spread. Sometimes you use mean preserving spread just to mean that specific second definition, but it's all equivalent. And so this is what I mean by increasing risk. All right. Just fix that. Okay, and so then we can use, so now we can use this definition of increasing risk to do comparative statics over risk. So we can use this first, kind of the first definition to think about how to do comparative statics over risk. And so all risk averters prefer y to x. Okay, so this is saying that, so x is riskier than y, and by definition, the expected utility of y is greater than the expected utility, of x for all concave u. Right, but this actually doesn't say we're using u because we defined it with utility functions, but really these are just functions. Okay, so this is equally true. So if x is riskier than y, then we can use a different name. We can say the expected value of g of y is greater than the expected value of g of x, as long as g is concave. Or you can also turn it around and say the expected value of g of u is less than the expected value, probably should be less than or equal to, of g of x, as long as g is convex. And so we can use this, right? So what this is saying is that the expected value of a function is decreasing in risk if that function is concave. Okay, and the expected value of a function is increasing in risk, x, right? It's increasing in risk if that function is convex. And so in order to understand the comparative statics of risk and uncertainty, it turns out what we end up having to do is figure out if the function we care about is convex or concave. If the function g here is neither convex nor concave, then it means that the expected value is ambiguous in risk. And so what that means is that with some increases in risk, the expected value will increase, and with other increases in risk, the expected value will decrease. So if a function is concave, then we have a non-ambiguous answer. If it's convex, it's not ambiguous, but if it's neither convex nor concave, then it's ambiguous. Okay, if it's both, right, if you're both concave and convex, we're back to linear, and the expected value of the function doesn't change depending on this. So we can use this to do comparative statics. Okay, so this is actually just what I was just saying. And so this comes from, this is the Rothschild-Stiglitz paper where they came up with this. And so, let's see where we are. Okay, so then I'll come back to this in just a minute where we can use this. And then I'm just going to take just a slight side. So that was specifically increasing risk in the Rothschild-Stiglitz sense. But there are a number of other definitions of increasing risk, and you can do kind of similar analyses of definitions as well. And so for each of these, they have multiple kind of equivalent definitions. And so first order stochastic dominance just says that y dominates x if all increasing utility, if expected utility for all increasing utility functions is greater for y than for x. So the difference in first order stochastic dominance with the one we already saw is here the utilities are increasing and they don't need to be convex or concave. In a mean preserving spread that we saw, it just had to do with concavity, didn't actually say about increasing. Okay, then it has, just like we had that integral condition that showed about the tails being heavier, this has a similar equivalent integral condition as well. And then second order stochastic dominance is almost exactly like risk, but it's expected utility of y is greater than expected utility of x for increasing concave u. Okay, what happens then is that the mean doesn't necessarily have to be equal. So we can compare different distributions that don't have an equal mean that way. Okay, so the difference again, the one that I defined with increasing risk was just concave u. It wasn't stuck with increasing. And then there's third order and so on. Each of the definitions again have these equivalent integral conditions having to do with their CDFs. And then there's also some work where using prospect theory, you can look at increasing S-shaped and reverse S-shaped functions and various other aspects. There's a lot of different ways you can do it. Okay, I'm going to focus on just the Rothschild-Stiglitz increasing risk, but this is just a brief overview that these exist. Okay. So now this is how we can apply it. So I have, it's not entirely generic, but a fairly generic decision problem. We have a decision variable x, we're trying to choose x. We have benefits from choosing x, and we have a cost from choosing x. We're, in this particular case, just to make it easy, we're uncertain about the benefits. Okay, the random variable is z, so our benefits change depending on z. So we want to choose our x to maximize that objective function at the top. Okay, and so we just can take our first order condition and we see when the expected marginal benefits are equal to the marginal cost, and we have our optimal decision. And so now we want to know what happens to our x as we increase the riskiness of z. And so, well, what happens to our first order condition as we increase the riskiness of z? Okay, it's going to affect this over here. So we'd like to know, are our marginal benefits going to increase or decrease in risk? Because if they increase in risk and everything's kind of well behaved, then we will increase our optimal value of our decision variable. Okay, and so from what I said earlier now, how do we figure out if our marginal benefits, if the expected value of our marginal benefits will increase in risk? How can I figure that out from the definitions I just gave? So what do we want to look at? So how do you tell if the expected,
Sorry.
Go ahead.
The concavity or convexity of B.
Right. So we just need, what we need to check is that not B, but the marginal benefits, right?
Sorry.
So the marginal benefits, the partial of B with respect to x, that's a function. It's a function of z. Now we need to check if that's concave in z or convex in z. So if that's concave in z, right, if the partial of b with respect to x is concave in z, then the expected value of that function is decreasing in risk. And if that's happening, then our optimal decision x is the value of our decision variable x will decrease in risk. If the partial of b with respect to x is convex in z, then the expected value of the marginal benefits will increase in risk, and our optimal decision will increase in risk. If we look at the marginal benefits and they're neither convex nor concave, then we have to say it's ambiguous, and that our optimal decision variable will depend on the specific change in the probability distribution. Okay, and so that's the basic way that you apply this theory to get the comparative statics of uncertainty. So we need to check whether this partial of B with respect to X is concave or convex in Z. If it is, then we can have a nice unambiguous answer, and if it's not, then we know that the answer is ambiguous. Okay, and so this is just the same problem now with okay, it didn't work. So in this problem now, we now just have a two-period problem. So now we have a near-term decision x1 and a downstream decision x2 in this problem. So we make our near-term decision now, we pay the cost for that now. Then we learn the value of our random variable, our z, because the next decision problem is inside the expectation. So we learn the value of z, and then we choose our second stage decision x2, and then we have our benefits depend on both of our decisions, our random variable, and both of our costs. And so an example of this in climate change would be we're making near-term decisions about, say, abatement, how much we want to reduce emissions now. We're uncertain about climate change. We think in the future we'll learn more. In this case, we have us learning perfectly, right? So sometime in the future we're going to understand climate change, and we'll be able to make more decisions about abatement at that point. And so our x2 would be future abatement, x1 is near-term abatement, z is the uncertainty about climate change. Okay, and so it's a similar problem. So we're trying to solve this problem for the near-term decision x1. If you take the first order condition and you apply your envelope theorem, you see that it's maximized when, again, the marginal benefits with respect to x1 are equal to the marginal costs. But in this case, the marginal benefits with respect to x1 are a function of the optimized x2, your second period abatement, or whatever it is, your second period decision, which is itself a function of z and of x1. And so the reason this is somewhat interesting is that even if your top problem is actually completely linear, everything can be linear and everything, the partial of b with respect to x1 will not be linear in z anymore, because your x1 responds to z and it induces a nonlinearity. And so the same thing though, then you would just want to figure out, this is concave or convex in z, and if it is, then you have unambiguous comparative statics. Okay, and then this just gets into this idea in climate change we're also interested in is if we expect to learn more, what happens. And so this is a definition of learning more. So I just repeated on the top the definition of increasing risk. On the bottom is a definition for learning more or more informative. And so it's sometimes called the Blackwell definition of more informative messages. Blackwell didn't actually come up with this particular definition, but then he showed, a lot like the Rothschild-Stiglitz paper, that it's equivalent to a number of other things. But similar to our definition of increasing risk, it's what risk averters don't like, this one says a signal Y is more informative than another signal if all decision makers are weakly better off with that signal. You have a question?
Just the equivalence of the upper definition you gave at the last slide where we had the marginal benefits. Wouldn't that rather be the marginal utility here then? Or how do you think about the problem?
So, yeah, I think I don't have...
So here you have the equivalence of the marginal benefit and utility, which would be... No?
So I'm not sure. So I don't have, there's actually no utility in this.
No, exactly. That's why I got my question wasn't precise because we switched from marginal benefits to utility, and I wondered.
Right. Okay. So it's
think about that.
Right. So that was that thing is that when we defined increasing risk, kind of used this idea of concave utility functions, but it turns out that that U can be any function, actually. And so I've actually gone away. So in this particular problem, like I said, it could actually be all linear. There could be no utility at all. But risk is still important. Even if this decision maker is not risk averse, risk still plays a role. So I've actually dropped utility. You can put utility in and solve the same. We can put utility around, say, the whole thing, and you can solve the problem. But you don't even need to have a risk-averse utility, a risk-averse decision maker anymore. Risk is still important, increasing risk. And so we just need to know whether the partial of B with respect to x1 is concave or convex. Does that make sense?
Yeah, I guess I'm also in the back of my head, I'm thinking that actually, if you think of B as utility, then risk aversion isn't the problem here because we're interested in the concavity of the marginal utility, and then we're talking about prudence and not.
Right. Well, that's why, yeah, exactly. Okay, so that's where this whole idea of prudence came up, is that when Rothschild and Stiglitz and so on started solving these problems, they found out that being risk averse did not imply that people would all move in the same direction with an increase in risk. And so then that got people, they weren't happy with that. They said there should be some way to think about when people will all move in the same direction, and that's where the idea of prudence came up. Yeah, so that's right. So I don't even use utility just because there's enough non-linearity in these problems without even risk aversion. And so you can't add risk aversion in, but I've actually been looked mostly at them without even risk aversion. So then this one, okay, so this is just slightly different. Now we're talking about a more informative signal. So Y is a signal. So Z is the thing we care about. Y is a random variable which is somehow not independent of Z. And so when we learn the value of Y, we've learned something about Z. And so again, Z could be something to do with the actual climate damages, and Y could be a signal we're getting about climate damages. And this is just a way of defining how one signal is more informative than another. And it's very parallel to our definition of increasing risk, in that, again, all decision makers here, so these are all U. And you don't have to think of it as a utility function, right? U is just a function. But if this is true for all U, then Y is more informative than Y prime. Okay, and just like in the definition of increasing risk, this is equivalent to other definitions. There's a very similar kind of convexity definition. There's another one I can't remember. It's but anyway, so there's at least 3 different ways to think about what it means to be more informative, and it turns out they're all equivalent. And so you can, then Epstein had a paper that was, again, very similar to this application of the Rothschild-Stiglitz, where you can figure out if the decision variable is going to increase or decrease in informativeness. It's kind of a very similar thing. You have to figure out if the partial of this B here with respect to x1, actually to figure out if it's convex or concave in the conditional probability distribution. Okay, so it's a little bit more of a pain in the neck to do. But it turns out that in at least some cases, you can do this a little bit simpler. So what I have here on the top is a problem with partial learning. And so we're trying to maximize x1. We are going to get a signal y. We're going to choose our second decision variable, and then we have our payoff. So that's a problem with partial learning. On the second line is the same problem, but with perfect learning. So you choose x1, you learn the value of your decision variable, and then you choose x2. And so if the u, this payoff function, is linear, or linear and a separable function of z, then these two are very equivalent in that the x1 star will increase in informativeness if and only if x1 star star increases in risk. So you can actually go back to just testing whether your marginal u is concave or convex in C. So if you have a problem, if you're looking at comparative statics and you have a problem, and it's either linear or kind of separable in the Z, if you say something about how it changes in increasing risk, you can actually just automatically say something about how it will change in increasing informativeness or expecting to learn more.
Does it hold true if the signal depends on your action?
Is it what? I'm sorry.
Does this result hold true?
This
signal quality depends on your action, your choice.
The signal quality, no. So this is for what do you call that? An exogenous signal, right? So this is for passive learning. Is that what they call it? Yeah, I don't know exactly what would happen with the active learning. This is for, if you can model it as this kind of passive learning where you're just getting a signal. So the signal does not itself change based on your actions. Okay, so then we can apply this to climate change. So what is our time here? So I go till 10:30? I have some work for you guys to do, so I might have to speed through this a little bit. Okay, so this is a very simple model of climate change, where mu is first near-term abatement, and mu2 is downstream abatement. We are trying to choose our near-term abatement, mu, and it's got a cost. We have, discount factor for the future. We've got our expected value over the future of our downstream abatement. So that's the abatement we're going to choose after we learn about climate change. And then the damages from climate change, which are based on the stock of emissions, minus what we abate now, minus what we abate in the future, and the damages from Z. And so that's a very simple model of climate change, but we can use this to think about the comparative statics of uncertainty in learning. And so if what we care about, we really want to know about the near-term abatement, then we can take the kind of first-order condition. And again, that second objective function, you can apply the envelope theorem, and it simplifies, and you get something like the marginal cost of mu needs to be equal to the discounted expected value of the D prime. Okay, and so we're in this situation where we have the expected marginal damages. We want to know if expected marginal damages are going to increase or decrease as our Z gets riskier. If expected marginal damages increase in risk, then our near-term abatement is going to increase in risk. And if expected marginal damages decrease in risk, then our near-term abatement, the optimal near-term abatement, will decrease in risk. And so we want to know what our marginal damages look like in terms of risk. And so we see before what that means is we want to know if our marginal damages are concave or convex in our random variable C. Okay, so this is a complicated problem. A few different people have looked at it. So if we just do it very simply, and so if we just assume a couple things. So if we assume, I think if C is quadratic and if D is quadratic in S, and then we the uncertainty is linear. So it looks something like Z, something along the lines of Z times S squared would be our damage function. Okay, in that very, very simple case, then we can look at the marginal damages. And so this is what they kind of look like. So this is the Z, which is some multiplier for the damages. It shows how bad our climate damages are. These are our marginal damages as a function of Z. And so it turns out that as long as damages aren't too high, these marginal damages are actually concave in this random multiplier Z. And the reason is it's a lot like the reason that the profit function is convex, right? It's that we're able to respond. And so, as if you kind of think of, you have some kind of marginal damages. As your damages get higher, then you respond. And you get higher damages, you say, uh-oh, we better pull back and reduce emissions more. And so the marginal damages, rather than kind of increasing linearly, which is what they would do since I'm just assuming a linear multiplier, they would increase less than linear. And so we'd end up with concave marginal damages. And so if you ignore this part I have over here, if you just assume that you can always reduce your emissions in response to learning about the damages, You can just always keep reducing emissions. Then we write a concave marginal damages. Expected marginal damages would decrease in risk, and our near-term abatement would actually decrease in risk. So the more uncertainty we had about climate change, the less we would do in the near term. Okay, in this very simple case, if you kind of ignore this constraint. Okay, so there's one paper, like, there's a paper by Karp, I think Karp and Jang and Jean, and they have a model just like this, and they ignore that constraint, and so they come up with this result and other results as well. But there might be this problem here. There might be damages that are high enough that we want to reduce emissions down to 0, or maybe we want to reduce emissions below 0, right? These damages, it turns out that they're really, really bad. They're catastrophic. We want emissions to be negative, okay? And so there may be a point at which, when I first started doing this, people hadn't thought too much about negative emissions. So now we think we can have some negative emissions. But there may be a point at which we just can't get our emissions below that level. So the damages are so bad that we would like to basically we'd like to go back and change what we had done in the past, right? So if there is a point at which we can't reduce our emissions anymore, then these marginal damages, in this very simple case, are going to continue on linearly. And what we end up with is a function that's neither concave nor convex. Okay, so it starts out being concave, and then it shoots up there. I don't know if it's very clear from this one. Okay, and so what that means is that what we do in the near term is ambiguous, that we can't really say whether we should increase our abatement or decrease our abatement as we increase in risk. And this is in a very super simple case. Okay, so there's a paper by Ulf and Ulf that came out in the Economics Journal, where they basically looked at this problem, and they showed it was ambiguous, and then they did this kind of funny thing where they said that, well, if the expected damages were right about at this point here, so the expected damages are high enough, then they show if you compare certain damages with uncertain damages, you would abate more under the uncertain damages. But it's not kind of generally true. It's a very specific case. But basically, the story is that it turns out it's ambiguous. And so you can add all other kinds of things on top of it, but it basically stays ambiguous. You can add a utility function around the whole thing, and you can make it very, 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 very prudent. And at that point, then you would optimally do more in the face of uncertainty. The more uncertainty you got, the more you would reduce emissions. But generally, it's ambiguous, and people looked at it now from a number of different directions, and it turns out that there's really not a lot of unambiguous answers there.
How about if you inserted uncertainty in the exponent of S?
So that, you can look at different things like that. I guess I'm not sure if I looked at that one specifically, but I'm pretty sure it still is going to come out at ambiguous. But you could look at it. A lot of people have done the Z, but they have done some where the uncertainty is not linear in the damages. It can be convex in the damages, and you still, again, you may be able to get, if you can force something to be convex enough or concave enough, you may be able to get it to be unambiguous, but it generally takes a lot. It seems to be, it's a pretty ambiguous answer. It really depends on the specific way that the uncertainty increases or decreases. All right, let me see here. And so that's kind of what the answer, there's definitely a literature out there. The basic answer is this. Unfortunately, when you look at it theoretically, we really haven't been able to come up with anything. That optimal emissions sometimes increase in risk, sometimes decrease in risk, sometimes increase as you expect to learn more, sometimes decrease as you expect to learn more. Theoretically, we just haven't really been able to get very far. And so it's kind of to the point where you have to start thinking a little bit about, do we actually know anything about the probability distribution over climate damages? Can we think about what we mean by increasing risk? Because the theoretical it's kind of gone to the end of where it can go. All right. So I want to talk a little bit about the role of technical change. All right, so we want to know what to do about climate change. So I've been focusing mainly on what the optimal emissions path would be. But as probably many of you in here are familiar with, the optimal emissions path depends a lot on the technologies that you have available. And so another thing we can think about is R&D. How much should we invest in R&D? What kind of R&D should we invest in? Is technology R&D a hedge against uncertainty? And so to think about that, especially if you want to think about how it relates to uncertainty and climate damages, you might want to model this looked at modeling it in a top-down model, okay? Because it's a little bit harder to get explicit uncertainty in a lot of these really technologically detailed integrated assessment models. And so a number of people have modeled technical change in top-down models. And it's interesting to look at the ways that they've modeled it. And so one way you can model it is you can just assume that technical change will reduce the marginal abatement cost. So math is marginal abatement cost. You can have technical change affect the cost of abatement. You could have technical change reduce the emissions to output ratio. You can have technical change, you can have knowledge basically be right in the production function. So as you invest in technical change, it's input in your production function. And then I've also done one where we use the profit function. So what's interesting about these is these different ways of modeling it have implications just on their own. And so it's kind of interesting to look at that. And so these are the ways, so up on the top there are certain ways of modeling technical change. And in these ways, your marginal abatement cost curve is lower after technical change everywhere. And so these are what your assumptions are. But, well, should we just go to this next one? Nevertheless, so they all lower the marginal abatement cost curve, but you get very, very different pictures of what the technical change does to the marginal abatement cost curve, which actually has an impact. And so you can think a little bit about how you're modeling technical change and the implications of these things. Moreover, a number of the papers that have modeled technical change, it turns out that the way they model technical change actually can lead to a higher marginal abatement cost over some pieces of the abatement cost curve. Not all of it, but over some of it. And so if it, say, pivots the cost curve rightward, if you reduce the emission to output ratio, if knowledge substitutes for fossil fuels, and some other things, these can lead to a higher marginal abatement cost curve. So let me show you a picture of that here. So this is, if our blue line is our cost of abatement, not marginal cost, but we have a cost of abatement. We have technical change. It reduces the cost of abatement, but it reduces it more at these lower levels of abatement than it does at the high level of abatement. So this is what our cost looks like. So you can see that what's happening is your marginal cost, which is your slope, has gotten higher at the high end. And so your marginal abatement cost curve looks like this. So after technical change, you have higher marginal abatement costs at the high levels of abatement. And so a number of the ways of modeling it gives you this result. And so at first people are like, no, they don't like this. But actually it's not an unreasonable, it's something that can actually happen, right? And so I think we're kind of seeing it right now with the this breakthrough in the shale gas, the fracking. Natural gas has gotten very, very inexpensive, so that's this big technical change. It's had a big effect on climate change. So it's lowered the cost of abatement, and it's certainly lowered the marginal cost of abatement at low levels. But when we think about climate change and wanting to possibly get to these very high levels of abatement, say maybe 100% abatement, if climate change is really bad, we're going to have to eventually substitute away from natural gas. Okay, we're not going to get to 100% abatement, or very unlikely, using natural gas. We're going to have to substitute away from natural gas. Natural gas is so cheap right now that it's going to be more expensive. It's more expensive and more painful to substitute away from it. And so it's going to increase our marginal abatement cost curve. And so this is something that can happen. So the thing about this is that in these models, these top-down models, so people are just making an assumption about technical change, but really they're modeling fairly specific types of technical change, right? This isn't solar, right? Solar is not going to have a shape like this. This is improvements in natural gas. And another thing you're modeling solar, and you're not modeling natural gas. So you have to be a little bit careful because these different technical changes have very different impacts, which add up to a lot of different things. All right. And so this is just showing, even if they all reduce the marginal abatement cost curve, these different types of technical change can have a very different impacts on how much you reduce abatement. So the black line is the marginal abatement cost curve before technical change. Blue is one type of technical change, and red is a different type of technical change. I have, these are if marginal damages are low, and up there I have if marginal damages are high. And so the blue line, so maybe that's an improvement in solar or something like that. What we see here is if marginal damages are low, it's really hardly affecting abatement at all. Whereas if marginal damages are high, then we're increasing from this level of abatement to a much higher level of abatement. Whereas the red line, marginal damages are low, that has a big impact on our optimal abatement, whereas marginal damages are high, it has a smaller impact. So the point just being that not all technical change is the same, and so we might want to think how specific technical changes should be modeled. Okay, so then this is actually, you can just look at this later. These are just a bunch of papers that have looked at endogenous technical change and uncertainty and climate change in various kind of pieces. And so this will be, I'll post this if you want this, and I have the papers later. Jump on. And so, but these are a whole bunch of papers that we've looked at. And so what happens, how does the investment, say, in R&D, how is that impacted by uncertainty in learning? And so you could probably kind of guess. It turns out that it's very similar to what we got before. If you just look at it theoretically, that the optimal investment in R&D, it can increase in the risk of climate damages, it can decrease in the risk of climate damages, it can increase or decrease in the uncertainty around the technology itself. So again, the theoretical work turns out to be fairly ambiguous, and it brings us back to this idea that we want to, that we need to maybe go a little bit beyond the theoretical explorations and think a little bit about what these probability distributions look like. And so that's what I'll be talking about tomorrow. All right, so before we go, we only have 5 minutes, but I have a little bit of work for you guys to do. Okay, great. So first I have let's see. Oh, that's this tomorrow. Okay. So first I have this one. So this is a questionnaire. This is just asking you some questions. So just hand these out. These are actually just some things. We're going to do a survey on these. So if you can just answer these questions, yes or no. So if they're anonymous, it's just a survey of different questions. Just answer those yes or no and hand those back. I'm going to do some questions on those. And then I have another thing for you to fill out. So just answer a yes or no, even if it's not. What? Sure. I'm not going to publish it. Okay.